In this clip, we're going to be looking at exponential functions. You might hear the word exponential or exponentially used in everyday life. Here are 3 examples of sentences using the word exponentially. It actually means getting bigger increasingly quickly, and this is what people mean when they use it in real life. Here are 3 examples of mathematical exponential functions and their associated graphs. You'll notice that in each one, the variable x is the power or the index, and the graphs all look similar. They get bigger increasingly quickly. Let's have a look at this graph now and look at this point here. This is the point where x is equal to 0. If I put that into the equation, I get y equals 2 to the power of 0. Now, any number to the power of 0 is 1, so that tells me that it must cross the y-axis at the number 1. Let's look at this one in the same way. Again, x is equal to 0, so I've got y equals 5 to the power of 0, and that's going to be 1 as well. So this crosses the y-axis at 1. In the same way, this one will cross the y-axis at 1 as well. This is a really important feature of this type of exponential graph. Just out of interest, if this number here is less than 1, then the graphs will look like this. Once again, on these graphs, the value here will be 1. So to summarise exponential functions, they generally look something like this, where the variable is in the power. The graph of an exponential function will look something like this, where it cuts the y-axis at 1. Another characteristic of these types of graphs is that they get bigger increasingly quickly, like this. Finally, as long as the function looks like this, the graph will never go below the x-axis. It will get closer and closer to it, like you can see here, but it will never actually meet or cross the x-axis. We say that the x-axis is an asymptote. This means that the curve will get closer and closer to it, but will never touch it or cross it. Here's a question for you to try. Press pause and have a go. When you're ready for the answers, press play. I'm hoping that you decided that graphs B and F were the graphs of exponential functions. Here's another question for you to try. If you find part B difficult, don't worry too much because I'm going to go through that with you afterwards. Press pause and have a go. When you're ready, press play. For part A, we want to find the coordinates of the point where the graph intersects the y-axis. That's here. Now we know that this is going to be 1 and it's at an x value of 0. So the point is 0, 1. Now for part B, I want to find the value of A. Remember, the function is y equals a to the power of x. Now if I can find nice values for y and x, I'll be able to work out what A is. Where on earth can I get nice values for y and x from? Well, I can get them from the graph. I'm going to use this point here. X is 1, which is a nice value, and I can see that y here is 3. So I've got 3 equals a to the power of 1. This tells me that a must be 3. Now I can check this by using another point on the graph. Let's use the point where x is 2. So x is 2 and y is 9. So I've got 9 equals, I think 3, remember, to the power of 2. Does this work? Yes, it does. So we're correct. The value of A is 3. In this more difficult question, I'm given the equation of a graph and I'm also given the graph. And I'm being asked to find what P and Q are. The first thing I notice when I look at my graph is that it's not crossing the y-axis at the number 1, because that would be here. And that's because the equation is not q to the power of x, It's p times q to the power of x. Let's look at this in a numerical context. So I've got y equals p q to the power of x. At this point here, x is 0. So that's p times q to the power of 0. Now I know that q to the power of 0 is 1, so that's p times 1, which is just p. Now from the graph, I can see that at this point here, y is actually a half. So I can replace the y with a half, and I get that p is equal to a half. Now I need to work out what q is. To find q, I'm going to use this point on the graph to help me. So I've got y equals p, which I already know, that's a half, times q to the power of x. At this point, x is 1, so I've got y equals a half times q to the power of 1. Now q to the power of 1 is just q, so I've got a half of q. If I can work out what y is, I'll be able to work out what q is, and I can find y from the graph. Looking across, I can see that y is 2. So 2 is a half of q. That tells me that q must be 4. I've now got the values of p and q, but before I finish, I want to check them. And I'm going to check them using one more point on the graph, this one here. Now, using the two values I found for p and q, I think that the equation of the graph is y equals a half for the p times 4 for the q to the power of x. At this point here, x is 2 and y is 8. So I'm going to substitute these into here and see if it works. So I've got 8 equals a half times 4 to the power of 2. Now 4 squared is 16 and a half times 16 is definitely 8. So this is correct. So my value of p is a half and my value of q is 4. Here's one for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Now this is a typical exam question where they haven't given me a graph. I'm told the size of an animal population on an island increases exponentially. I'm also told the rate of increase, that's 25% per year. I'm told that at the start of 2015 the population was 4,500 and I want to find out the size of the population at the start of 2010. To help me with this, I'm going to draw a timeline. So I want to know the population at the start of 2010. I know the population at the start of 2015 is 4,500. I'm going to call the population that I'm looking for P. Now I know that it increases by 25% per year. So from 2010 to 2011, the population will multiply by 1.25. The same thing will happen here and for every year. Using this, I can now create an equation. I have P times 1.25 to the power of 1, 2, 3, 4, 5 equals 4,500. This is where the exponential part comes in. You can see we've got a power here. I want to find P. So to do that, I'm going to do 4,500 divided by 1.25 to the power of 5. I can use a calculator for this, and I get an answer of 1,475 rounded to the nearest whole number. So the size of the population at the start of 2010 was 1,475 animals. Here's a similar question for you to try. Press pause and have a go. When you're ready for the answer, press play. Here's the answer. The key to getting this one correct is to realise that because the price of the car is falling by 35% every year, we need to multiply by 0.65. This is because if we start with a price of 100% and take away 35%, we've got 65% of our original price left.